Okay, let's talk about these strange RF devices. You may not have seen these before because they kind of operate at very high frequencies, and not a lot of people do things in their garage at these high frequencies. So the size of these things make me believe that they're probably about a 4 to 8 gigahertz type device. We'll talk about what they are, but I think these operate generally around this size. You know, I've seen them somewhere between 4 and 10 gigahertz, but I think these are probably up close to 4 gigahertz, that type of range. And they can be very narrow band. They're not a real broadband. They aren't really a broadband thing. So what are they? These are known as isolators. You can also call them a circulator with a load. Circulators and isolators work on the same principle. It's just that an isolator uses a circulator but puts a 50 ohm resistor on one of the ports. So they're a three-port device. There's an input, output, and then an other. And in this particular one, the other is kind of plugged up and it's got a 50 ohm resistor in it. Okay. And so, yeah, so what are these things? Well, I call them one-way valves, okay? If you put in, there's an input and an output. So if you put things in the input, they'll go through. And if you put things in the output, they don't go through. It's like a diode. It's like a RF diode. But they're not diodes. They're based off of a really cool electromagnetism thing, you know, Maxwell's equation type of thing. They're very, very interesting. So they work with magnets. There's actually magnets inside of here. It's the magnets that do the work, which is really, really bizarre. Let's we're gonna measure these. Before we do that, I found an article online, Microwaves and RF. That's kind of like the journal for this type of stuff. And they say, you know, here's a primer on circulators and isolators, okay? And I'm not going to talk a lot about these things because I don't know a lot about these things. I don't want to say wrong things, but I know enough to be dangerous. So this is a circulator. There's 3 ports, okay, 1, 2, 3, and there's this circle with an arrow goes around. So this is like a roundabout. It's like you drive here, and you have to go one direction. It says, you know, all traffic will go clockwise, right? And so this is the type of device that we have, right? Input, output, and this 50 ohms down here. So what it says is that you always have to go clockwise around the roundabout. So if traffic comes this direction, it has to go this, and then it can come out, okay? But if traffic comes in this direction, it has to follow the arrow, so it has to go this direction. What happens is it then sees this 50 ohm load, and it never makes it to the other side. And if things actually come this direction, they would go and come out this way. But since it's a 50 ohm load, everything's going to die here, and there's not going to be a lot to sneak out over there. So, yeah, so it's a magnetic roundabout. So before we go into what these things look like inside, I'm going to give you a real hand wave. If you've taken any physics or electronic theory and stuff like that, you'll hear something called the right hand rule. Okay, so if you have a wire, okay, so here's a wire, and you have current going in this direction. Okay, it makes a magnetic field, right? It's an electromagnetic wave, right? An EM wave. This electricity and magnetism, this E&M, always coexists, and they're kind of at right angles to one another, and they always coexist. And there's 4 Maxwell's equations. There's two in the E part, and there's 2 in the M part. Okay, and one of them says that you can't have a monopole magnet, and one of them says that anyway. Don't want to talk about Maxwell's equations. So if we have current going in this direction, we apply the right-hand rule, okay? So your thumb is the direction of the current, and then these fingers tell you the direction of the magnetic field. So the magnetic field will go in this direction, okay? This will go in a clockwise direction, this way, right? And that's the right-hand rule. It's just a quick way of knowing what direction the things are going to go. If current is traveling in this direction, then you do the right-hand rule, and you'll see it flows in the up, and the magnetic field will flow in the opposite direction, okay? So sort of imagine this. This is a big hand wave, but sort of imagine this. Your current's coming through this way, so your RF is going this way. So your RF is going this way, and it's setting up this is an electric field, and this is a magnetic field. And let's say that you have a permanent magnet in here, and that permanent magnet's in the same direction as your fingers. And so your fingers are very happy. You know how two magnets kind of repel each other or they attract each other? Well, if they're in the same direction, they kind of help each other, and everybody's happy, okay? So everybody can go through this way. But if we go through this way, and the magnetic our current goes in this direction, the magnetic field is now going to be opposite, and it's going to be fighting those magnets. So that there's a permanent magnet in here, and you have an electromagnet that you've set up, and they fight each other, and it just says, whoa, I just don't want to do that, okay? And this current just goes, and it says, okay, I can't go that direction, I'm going to be bent, and it's going to bend down, okay? So that's my really, really big hand wave. But just kind of remember that, you know, it's a magnet thing. Okay, so they kind of look like this, okay? They actually have like 120 degrees thing apart. And this is the roundabout. So if you have a clockwise roundabout, then if you come in here, you have to go to this one. And if you come in this one, you have to go to this one. And if you come in this one, you have to go this way, okay? And so even though this kind of looks like a T, it's not. It's actually this the shape inside, okay? And two of them connect here, and then one of them connects down here, okay? And so I might open one of these up. I don't know if we can see inside this or not. We could try. And so that's the isolator. I mean the circulator. Okay. And then, like I said, to build the isolator, you just have to put in a resistor. Okay. So there's a resistor here. Okay. So I think that's kind of enough. You can read up on it online if you're really curious about what's going on in here. There's actually two permanent magnets, and there's ferrite in there, and then there's a strip line on a dielectric that has that roundabout pattern on it, and then all of the magnetic fields get set up in this thing, and the ferrite discs help with the fields and stuff. And yeah, it's very complicated. It's not that kind of black magic stuff in RF land. So yeah, so circulators, isolators. So let's take a look at our isolator. All right, so I want to do a measurement. Okay, I want to do two measurements first. If you buy an isolator, you buy it with a couple things in mind. One is that it has to have the right frequency range that you're interested in. The next is that you have to be aware that there's going to be some attenuation. There's going to be some insertion loss, they call it, okay? So we'll measure the insertion loss at this thing, at the frequency we're going to test it at. And then we're going to turn it around and see if it rejects any. Now, like I said, this is probably something around a 4 gigahertz type device, and I really don't have the right test equipment to show you its full capability. Usually, the isolation is going to be around 18 dB. 20 dB is a really, really good one, but about maybe 18 dB of attenuation. So if we measure it with something lower than that, I'm going to be measuring it at 1.7 gigahertz, okay? And at 1.7 gigahertz, it should be a little bit, okay? There'll be a little bit of that magnet. And we should see some attenuation, not the full 18 dB, but we should see a little bit. And so we'll go measure that. We'll also measure the insertion loss just because we can, okay? All right, so that's what we're going to be doing. If you're playing along at home, this is an E&M Laboratories, Westlake Village, California. Model number S12T82. I couldn't find a data sheet on this. Maybe somebody can find one for me. S12T82, and that's a serial number. So this is the 537th unit they built. And yeah, I've seen tons of these used in the industry. But yeah, let's go measure it. Okay, so we need a function generator, and this one can go up to the frequency range that I need. So I'm going to set it at 1750. 1750 megahertz, so 1.75 gigahertz. And so we're going to output that on this cable, all right? And then the first thing we're going to do is we're going to zero our instrument. So we're going to put in a feed through here, and we will zero the instrument out with this, and then we will then substitute this in here and measure its insertion loss. and then we'll turn it around and measure its insertion loss the other way, okay? So let's do this one first. All right, so we have our, bump the camera, we have our signal over here. So let's zoom in on that. Let's do peak search, center frequency, and so there's our center frequency, and then we can do a peak, and we can do a marker to reference level. So I've set the very top of the instrument to this high. This isn't very tight here. Tighten these down. Make sure all my connectors are tight. Okay, so we'll do that again. Peak search, and we'll move that to the reference level. Okay, so we are in the center and at the top reference. So if there's any, so now I'm gonna take out the little feed through here, and the signal should go down and then disappear. Take it out. Okay, good. All right, now if I can disconnect this. Oh man, this is on tight because I said to put it on tight. Let me get a little wrench out here so I can take off this thing. Okay, so now I'm gonna put in the put it right way around. I'm connecting the spectrum analyzer to the output, and I'm going to be connecting the generator to the input, and you can see we're back up again, and you can see that we've got very little here. So let's go ahead and change the scale here. Amplitude, let's do scale 1 dB. So we'll have 1 dB steps, okay? So we were down 2 dB. So the insertion loss is 2 dB at 1.7 gigahertz. So let's bring that up to the top again. Okay, so these are 1 dB steps, all right? And we're at the very tippy top now. And then I'm going to turn the isolator front to back to front. Okay, so the input's now the output's now the input, and let's see what kind of attenuation this thing can do. Like I said, you know, if it were on the frequency it was designed for, it'd be around 18 dB down, but this is not anywhere close to what this thing was designed for, so it's going to be not as good. And we bought so 1, 2, 3, 4, 5, 6, 7, 8. So it's at least 8 dB down. Oh dear. So let's change the amplitude. Okay, let's do scale. Let's do 2 dB steps. So 2, 4, 6, 8, and a little bit. So yeah, not so bad, right? So just so you believe me, I'm going to take the isolator and I'm going to swap it around again. All right. I'm going to do input to input and output to the spectrum analyzer. And there it is, back again. So we have 8 dB of attenuation for this circulator, and it's not even designed at that frequency. So, yeah, it's pretty cool. Like I said, it'll probably do 18 dB where it's designed for, but 8 dB is pretty good, right? 8 dB, that's a lot. You can get these in all different sorts of frequency ranges and stuff. So before you run out and buy one, be aware they're $300. So, yeah, to buy a brand new one, microwave stuff is very expensive, but to buy a new one of these is $300. And so here's $600 sitting here. So, yeah, thanks, Bill, for the donation. So, you know, I don't have any use for these, and these were given to me no strings attached. And I think the very most valuable thing I can do with these is tear them apart and do educational videos. And so let's go ahead and take one apart, and maybe we'll all learn something together, okay? Well, there we go. All the screws are out, and I can see a slight parting line here. I think we can reach in there with something, and oh, there we go. I can reach in there with my fingers, and it's parting. So, oh, there we go. So we're taking this off. Oh, there we go. So this is just a magnet on one side, and this is aluminum. So the magnet doesn't stick through all the way. There's like a thin layer here with a magnet on that side. And then here we can see the two ferrite slugs, and we can see that 120 degree angle here. And oh, it's coming out. Great. Great. All right, so that came out of there. All right, so here's our device. And do these lift off? They might be glued. But before we go too much further, there's some little things here. I don't know what those are. Those are just spacers, I think. I think those are just little spacers. Yeah, I can pop those off. Let's do that. Pop these guys off. There we go. Sweep that out of the way. All right. Now we have one thing left to do, and that's to take this ferrite on. So do people get the idea there? There's a magnet on this side, magnet on this side, just like the picture. Right? Magnet, and then two ferrite things. And here's the ferrite. Here's the ferrite. So now we just need to get them apart. And let me get a really thin screwdriver. This reminds me of a story. You've probably heard it. Oh dear, yeah, I think these are glued together, so this might take some force. Anyway, the story is during the Manhattan Project, they were working on how much is a critical mass and all these other things, and they had a demonstration where they had two hemispheres, and they'd bring the hemispheres together, and you get a spike in the radioactivity because it would start to generate more and more as it was doing its fission. And at one point, the guy was using a screwdriver, and the screwdriver fell out, and the two halves came together, and there was a blue flash in the room. The blue flash is the Smirnov radiation, I think. You see it in swimming pool reactors, and swimming pool reactors is a blue glow, and it's where the particles are. You see the speed of light shock wave or something. Anyway, I'm not quite sure about all that physics, but anyway, there was this blue flash, and everybody in the room was told to stay still, and they marked their location on the floor with chalk and tried to figure out what to do with these people at the hospital and see if they could save their lives or not. Anyway, the story is, though, I think people have heard that part. Story is, my buddy who worked at Lawrence Livermore, his lab mate said, I was in the back of the room. I saw the flash. Oh, God. Yikes. Probably not a story you wish you had in your arsenal, but he did. I think this is glued together, so I'm going to have to... Anyway, before we go too much further here, you can see this is a 50 ohm resistor over here. In fact, let's measure it. Somebody was asking about dummy loads the other day, and not all dummy loads are created equal because it's hard to find exactly 50 ohm resistors. Most of the time you use 200 ohm resistors in parallel. Sometimes they'll use regular 51 ohm resistors or 52 ohm resistors and say, yeah, that's close enough. But if we go here, let's see here, ohms. If we go here and here, we should see, why am I not reading? There we go. I must not have clicked it right. Yeah, there we go. We are reading. I need to get the good connection here without being in the camera. We have 66 ohms. So it's probably some of that voodoo magic again. It's probably, there's also some inductance and reactance and stuff, and when you have it all together, it looks like 50 ohms. But if you measure it at at DC, it's about 70 ohms. So that's interesting to know. Okay. Yeah, let me work on getting this part. All right, I thought I'd get this in camera because it's probably going to be a spectacular failure. But I did take the connectors off. I desoldered those, and I took the dummy load off, which looks like it might be good for maybe 5 watts or something, at least 3 watts. So yeah, when you buy these isolators, you have to pick how much the load resistor can handle. Is it a 100-watt isolator? Is it a 1-watt isolator? All right, so now we have this thing, which is our roundabout. And I was thinking I would put it on something like this and hit it with a hammer. What could go wrong? Oh man, what could go wrong? Whoa, it's on there pretty good, huh? I'll just keep hitting it harder. There we go. Oh dear. A perfect solution to every problem is a hammer. All right. Yeah, so we have our ferrite here, shards of ferrite, and here's our little roundabout. And I think that's it. I don't think there's any other magic. I think it's just stamped metal. I think that's it. It's silver plated, right? It's nice, but that is it. There we go. It's just metal, see? It's just metal. So, it looks like a dead short to all 3 connectors, but in RF land, it isn't. And we have the RF police in a magnetic field. When the traveling wave comes in, it sees that magnetic field that's already set up, and it says, "Whoa, I don't want to go that way. That's too hard." And those 2 magnets like hit up against each other and go, "Whoa, no, going this way, going this way." So yeah, that's all it is. So isolator. So I think it was cool. It's exactly as you see it in the book, except for the 70 ohm resistor. That was a surprise. But I think if you've been around RF long enough, you know that you need to impedance match things, and you don't always use a 50 ohm resistor. You might have some inductance and some capacitance that you have to balance. And yeah, there you go. So here's all my carnage. All right. 1 dead isolator.